Hello and welcome back, everybody. This week we're going to be going into Chapter 3, but before I begin, what I'd like to do is go over a little bit of information that I covered last time in the lecture videos on research in psychology. There are two particular methods that I want to highlight. One, correlational, and two, experimental methodologies. What we learned last week was that correlations are useful for identifying patterns. That is, if you want to know that one variable is related to another, you can use a correlation. If you simply want to know that that association exists, that is what a correlation is for. However, its great limitation is that you cannot infer causation. That is, simply because two variables are mathematically related to one another doesn't mean that one actually has an impact on the other. For example, we could say that if we measured the number of masks that someone wears during the COVID-19 pandemic and the spread of positive cases of COVID-19 could be statistically related, but it wouldn't be enough to simply record the number of masks and compare it to the number of positive cases to be able to conclude that masks cause a change in the spread of COVID. What you would need to generate that kind of evidence is an experiment. That is a situation in which you manipulate one variable while controlling for others to see how manipulating that variable affects your outcome, whatever you think that it's going to impact. From this, you can infer causation. When you're designing an experiment, which I want to go into in a second, you need to identify independent and dependent variables. So this is a distinction that I will expect you to know and to carry on past the exam that you had to take. Remember that the independent variable is that which you expect to manipulate within an experimental design, or the variable that you think will predict change in another, that will cause change in another variable. And the variable that is impacted is then the dependent variable. Another way to understand this is as the outcome variable. And then I also want you to keep in mind the difference between random sampling and random assignment. These are important for any experimental design, but especially for an experiment when you're really trying to say something about causation. Random sampling is that every participant that you are sampling has an equal opportunity to be in your sample. So everyone from the population that you are sampling has an equal opportunity to be in your study. Whereas random assignment is once they're already there, once they're in that study, do they have an equal chance of being assigned to, say, one experimental group versus another, versus a control group or a placebo group? So I want to get into experiments a little bit more because these really are the gold standard of science. If you want to judge the quality of any information that science has produced, I would say experiments are some of the top-notch, high-quality examples of how to do science well. And it's because it is the research design that allows you to conclude that one thing causes another. Now, there are advancements in causal inference that there are other techniques that have been developed in addition to supplement experiments in being able to conclude causation, but this is still considered quite standard and the gold standard, like I said. What these involve is you must change an independent variable to see how doing so affects a dependent variable, and this is key, while controlling for or accounting for all other possible third variables, or at least as many as you possibly can. What this allows you to do, so compare this to something like a correlation where, let's say that we're standing outside a Walmart and we're counting up the number of people who walk in who have a mask. It could be, and then we look at how that's associated with the number of positive COVID cases within that county where we're sampling. It could be that there's a third variable impacting the relationship between the number of masks people wear and the number of cases. For example, it could be that people are really likely to wear masks when they're in Walmart, but maybe not so much when they are elsewhere. So could it be that, for example, people are more likely to spread COVID among their immediate friends and family, people that they interact with a lot, compared to those who are in these larger open public spaces? That is a third variable that might impact the relationship between the number of masks people are wearing and whether COVID spreads. So if you're going to ask a question like that, you need to specifically just manipulate the thing that you wish to change and account for all of these other variables in whatever way that you can. So I know that that's a lot. Let me break this down. I want to go through an example experiment because what you're going to have to do is design your own experiment for testing the hypotheses that you've been identifying, that at least you've identified last week. So let's take this question, the one that we've been playing with, the one that I promise I'm going to stop talking about soon. We'll move on to fresher stuff. But just to keep it really clear, really consistent, let's ask this question. Let's say that this is our research question. How might we experimentally test whether wearing masks, prevent the spread of COVID-19? Whatever your research question may be, these are the steps that I recommend you go through to identify everything that you need to know to design an experiment well. First, you need to identify that independent variable. What do you think causes change in something else? In this case, it's going to be whether people are wearing masks or not. The thing that you expect is going to affect your outcome, that is the spread of COVID. So your dependent variable is going to be that spread. Now remember, when you are designing an experiment or when you're putting forth a hypothesis, it's first very important next to operationally define your variable. That is, define it in a way that can be measured, that can be counted up, that can be split into groups, into distinct groups in the case of an experiment. So how would we operationally define these variables in a way that could be used in an experiment? Well, if we think back to what an experiment entails, that is splitting people up into different groups, an experimental group and at least one control group. What we'd need to do, I think, pretty obviously, is we could have people in the experimental group be asked to wear a mask whenever they go out in public, for example. Versus we'll have our control group also be going out in public, doing all the things that people in the experimental group would be asked to do, except they're not going to be asked to wear a mask. Now, we are going to assign whether they are in one group or another, and of course that should be randomly done. But what's important about that is that we're not allowing people to self-select into either wearing a mask or not. You can't have people come into the experiment already being in one group or another. So they're going to be randomly sampled from the population. They're going to be randomly assigned to one of these two groups, and then they will be asked to engage in that behavior or not, either wear the mask or not wear the mask. How would we operationally define our outcome variable, our dependent variable? Well, we could very simply look at whether they get tested for positive for COVID after a period of time. So then once you have your variables operationalized, that is defined in a way that can be measured, you then state what your hypothesis is. And your hypothesis should always begin with, I predict. Because you are making a statement about what you anticipate will happen when you've run this experiment. So in this case, you might say something like, I predict that people who are asked to wear masks and then interact with the public for a period of a month are going to be less likely to test positive for COVID than those who do not wear a mask. Notice that when I wrote this hypothesis, I used the operationally defined variables, that they're going to be put into one group or another, and the positive COVID test. I didn't simply say the spread of COVID. I said you would observe more positive COVID tests in the no mask condition, in the control group. What I will then want you to do in your experiments is describe what participants will be asked to do. So really itemize and go through every single procedure. I'm going to recruit X number of people, say 20 people from South Carolina, from the general United States. I'm then going to bring them all into my lab. I'm then going to give them the instructions in this lab about what they need to do. Either they're going to be asked to wear a mask or not wear a mask, that they must do these consistently across time for, say, a month. Important to specify time. And then at the very end, specify that they will be asked to take a COVID-19 test to see if they test positive for COVID-19. That's asking them what to do. Then, at the very end, you should also ask yourself, what third variables do we need to account for that we're not accounting for already? For example, do we need to confirm that people are spending an equal amount of time outside and actually interacting with the public? Is that something that you should measure to at least account for, to make sure that your groups are actually equal on this? Because maybe by chance, there are just certain people within your sample. It happens to be that the people who were assigned to the mask condition are also the people who really like to stay inside. So maybe they are experiencing fewer COVID, they're getting fewer positive COVID diagnoses because they're just simply not coming in contact with other people. That is something that you should account for in your research design. So think about those third variables. What else might impact the results that you observe? All right, this is my first example. I'll give you another example. Let's say that we have this question. How might we experimentally test whether marijuana changes intelligence? Now, I think this is actually an important question to answer because more than ever, THC products, so THC is the active ingredient in marijuana. With the greater availability of these products, we might want to start looking more seriously at some of the more common beliefs that exist about those who do ingest THC. I think one of the common stereotypes is, well, these people might be dumber somehow, or smoking, ingesting THC interferes with academic achievement, educational attainment. This is, I think, a particular research question that people are divided on, that we would want more accurate answers to. So how would we go about doing this? Again, let's run through our steps. First, we have to ask, what is the independent variable? And in this case, we think that THC dosage is going to somehow cause change in intelligence. So we think that marijuana is the thing that we want to manipulate, that we want to change in some way. And then the dependent variable, the outcome, the thing that we think THC is going to impact, is intelligence. All right, now here's the tricky part. How do we operationally define these variables? Remember, we must define them in a way that can be manipulated or directly measured. In the case of THC, what you may want to do is, again, divide people up into an experimental and a control group. However, when it comes to things like drugs, things that you could administer in different dosages, it's often a good idea to account for to include multiple experimental groups. So that is, maybe you'll randomly assign people to have a relatively high dosage of THC or a relatively low dosage versus a control group. What that allows you to observe is, well, maybe it matters how much you consume. Maybe in moderate quantities, it's relatively less harmful to your educational attainment than it is at relatively higher dosages. So to operationally define our independent variable, we may say we'll create 3 different groups. We'll have two experimental groups and a control group against which to compare these 2 other groups. Then in terms of intelligence, how would we operationally define intelligence? Well, there is a standard way to do it, and that's through something called an intelligence quotient test, an IQ test. Anyone who has ever taken an intelligence test before, if you've taken one online that you just found on social media, it may not be a real intelligence test. But there actually are the Wechsler's test for children, Raven's matrices for adults. Each of these assesses intelligence on a scale that is centered around 100. So the mean score, the average score for an intelligence test in the whole population is 100. From there, depending on how you perform, you either score relatively higher, I guess according to my camera now, I'm looking lower than average or higher than average. How they do this is they actually give you these puzzles. What they do is they'll have you solve a puzzle. They'll ask questions for you to perform certain mathematical operations, and then they'll usually time you and assess you for accuracy. And presumably, by doing things more quickly and doing them accurately, It's a sign of intelligence. Now, very broadly speaking, intelligence is generally considered your ability to adapt to and learn information that is unfamiliar to you. So it's how flexible are you? How able are you to adapt to situations that are unfamiliar? Now, this is actually to some degree what school does for you, right? Is you're asked to take these several different classes about different subjects that may be more or less familiar to you, and then you're expected to learn this material and be able to apply it or be able to show that you know it. Your ability to adapt to that situation that is unfamiliar to you is a sign of your intelligence to some degree. Of course, among many things, interest, of course, contributes to school performance, and there's all kinds of variables, but intelligence does factor in. Okay, so once we've operationally defined our variables, now we have these groups that we're going to manipulate, and we have the outcome that we're going to measure. Let's say we used an IQ test. We can now create a hypothesis. So I predict that people who are assigned to the high dosage THC group are going to score lower on an IQ test than those who are low dosage or those who are in the control group. Remember, your prediction should be a statement about the relationship that you expect between your two operationally defined variables. Then run through what you're going to ask participants to do. I'm going to collect X number of participants. I'm going to randomly, through random sampling, I'm going to randomly assign them to each of these experimental or control groups. I'm going to ask them to consume a certain amount of THC or not, and then I'm going to make sure to specify the time frame for which you're going to do that. Are you going to have them just smoke right there in the instant? Are you going to have them take an edible? And are you then going to assess their intelligence right away? Or are you going to have them do it for, say, the span of a month and then measure their IQ afterwards? In that design, you could measure IQ beforehand, measure IQ afterwards, and therefore you would see if there is a change due to your intervention across time. So make sure that you specify these details. And again, think about what third variables may exist. Is there some other reason that ingesting THC and having a particular IQ score would be connected to one another? Something that you have not accounted for. Be sure to think this through when you are designing your own experiments. All right, so what I will do is in my interlude video after the first set of sections, I'm actually going to have another example in there, run through this one more time just to make sure that everything is crystal clear. But I encourage you to start thinking about this. What are you going to do for your research proposal? Which hypothesis do you want to develop further? You, of course, are free to, I encourage you, please, to ask me for help. I'm here. If you're unsure whether you're doing it correctly, email me, say, hey, listen, I had this idea. I wanted to make sure that I'm doing this correctly. I am here to help, and I'm happy to set you on the right path here. So make sure you start thinking about that. All right. All of that stuff aside, which is really just getting you ready for the assignments in the future, now begins our introduction to Chapter 3, the biology of psychology. Now, I want to start this section by saying that I love biology. I'm one of those people very early on. I was attracted to biology. I just think that it's having a biological understanding of the world, I think really adds a level of depth to almost everything that you can possibly learn. And I would argue that it is absolutely necessary to understand psychology. Now, I am sensitive to those who do not like biology as much as I do. I think that the information that I present in my lecture videos, it is presented at a level that I think that anyone could understand it and appreciate it. Of course, what I'm going to do is I think that this knowledge should be applied in some way. I don't want you to just know the biology for the sake of biology. I think that it's important for understanding how your psychology works. And the reason I think that is, well, your psychology is housed within a physical, within your physical body. It is part of the mechanical world. Your psychology does not exist separate from your body. So we have to understand the biology, particularly of the nervous system, to understand how that nervous system produces psychology, produces the sense of, say, a self that you have. this personal experience that you're having, or the internal thoughts that you have. How can you produce that from the nervous system and the many interactions that your nervous system has with other parts of your body and the outside world? All right, so I'm putting a lot of weight on the nervous system here. Why? What does the nervous system do for you? Well, there are two main functions that I want to emphasize in this class. One, and this is what you've probably learned if you've ever gone over the nervous system, had an anatomy class, learned anything about psychology before, you probably just simply learned, okay, it communicates information. It's responsible for taking information from point A within the body and transmitting it to point B. So that is, if there's light all around you, if there's sound out in the world, if there are things that you can taste or smells that you can detect, your nervous system is going to be responsible for taking that information, that light information, sound information, and transmitting that information from wherever it's going in, whether it's through the fingertips for touch, or your ears for sound, or eyes for light, transmit that information to your brain in such a way that your brain can interpret it and then produce some kind of output, produce some kind of response based on that information. That's what your nervous system is meant to do. The basic function. Another function that I'm going to highlight in this class is that your nervous system exists. It tries to make predictions. So rather than just communicate information, your nervous system is actually constantly changing depending on what information it receives. And with that changing information, it tries to make predictions about the future. So, for example, you might take in, let's say that you're in front of a hot stove, you're cooking something, you put your hand on that hot stove, the temperature information goes from your fingertips up to your brain. Your brain says, this is a sensation that might be damaging me. This temperature is too high. My skin is probably burning. And so it sends a signal back down to your hand saying, pull it away. Well, it doesn't just do that. Now, in the future, next time you are around a hot stove, you're going to be more likely to do what? Not touch the stove in the first place. Your brain, your nervous system starts to predict that, stoves tend to be hot. They tend to damage me. So I'm going to predict that I shouldn't touch the stove while it is red. That is a prediction. Your nervous system makes predictions. To make predictions, there's a very basic concept taken from mathematics and from computer science, largely, called heuristics. I think before I set you loose on chapter 3 and all the biology that I want you to learn, I think it's important to introduce what a heuristic is. It's a simple, efficient way of solving a problem. Very commonly, you might refer to it as a rule of thumb. That is, what do you tend to do in a particular situation? So given that you haven't encountered something before, something it's kind of life and death, it's very sudden, what do you do? What do you automatically do? What's your default response? So let me give you a solid example of this. Imagine someone starts choking. What is your heuristic in this situation? Well, if you've grown up and you took CPR classes, or I think most in elementary school, middle school, those who are in Boy Scouts, many different places, they actually teach you something called the Heimlich maneuver, right? If someone's choking, and first off, if someone is entirely choking, that is, their airway is completely blocked, you should be doing the Heimlich maneuver. If it's partially blocked, you're actually supposed to let them try to cough it up, because that means there's still air getting through and you can actually do more damage with the Heimlich than it's helpful. But if it's a completely blocked airway, what you're supposed to do is they teach you this early on, and it's a very standardized practice because they don't want you to have to hesitate. What you do is you put your arms around someone, you make a fist with one hand, you try to tuck your thumb into your index finger so that you create a flat surface right here. You don't want it jutting out, because you can cause damage that way. You make a flat surface, you then take your other hand, put it here, put that flat thumb surface on the bottom of your sternum, right there, and then push inward and upward. And the idea is that you want to compress the chest cage, compress the rib cage. You want to compress here so that the air within your lungs gets compressed and pushes on whatever's lodged in the throat. That's the Heimlich maneuver. You want that to be an automatic, relatively simple rule of thumb for what you do when someone is choking, because in that moment, you might not have time to think about it. If you're fumbling around with that, someone could choke. Speaking of immediacy, let's imagine that you are out hiking. I don't know how many of you are outdoors people, but imagine you're out in nature, you're having a good old time, you're hiking around, and you're on this trail, and then next to you, there's a bush, and it starts to rustle. It seems like something's in there. Something's moving. What do? What is your heuristic? What is your automatic rule of thumb? For most people, it is you stop moving. You orient your head towards whatever it is that you orient yourself to the bush, and then you pay attention. Why? Why do that? Why have that be the automatic response? Well, if this is something that is threatening to you, it's important to have a surprise response that then is followed by you evaluating, is this actually a threat or not? You see this as a response. This is a heuristic that is built into the nervous system from a very early age. Babies do this. Infants do this before they've necessarily had someone, a role model, show them. If they are suddenly surprised, there's a loud noise, something moves, or they see something that they did not expect, what they do is they stop, they look at it, and then they just analyze it, and they look at it for as long as they need to feel relatively safe about it. And then if they don't feel safe about it, what do? They start to cry, they turn around, they start to try and crawl away or move away, they ask for a caregiver because it's something that's potentially dangerous. That is a good rule of thumb, is to be surprised and evaluate, pay attention to something that is unexpected. Now, a lot of heuristics like this are there from early on. Now, there are a lot of heuristics that you learn. The Heimlich maneuver you had to learn if it is a heuristic that you have, but a lot of them develop early on or are heavily influenced by biology. Let me give you an example of this. Infants, from very early on, if anyone works with infants, you probably tried this before, where you're trying to play with this little kid, entertain them, all that stuff. And they have their little foot, and if you graze your finger along the bottom of their foot, what do? They curl their toes. That is a heuristic. It's a reflex in many ways. It's a very basic heuristic, and it's one that's there from very early on. The idea is that this may have at one point played a protective function, if it still does not. The idea is if you are, say, holding an infant, and that infant starts to slip, and it is going to then feel stimulation where it did not feel it before on its feet or on its hands, as it starts to slip. Having this response where with your palms or with your feet you start to grasp could actually create more friction, prevent that child from falling or have them fall more slowly, give more time to the caregiver to hold on to that child. Imagine the alternative. If the child didn't do anything, didn't try to, the other thing that it'll do is when it's surprised, it'll put its arms out. Children tend to put their arms out. That allows a caregiver to grab them more easily. Imagine if they didn't do that. They'd just be this smooth little bullet that could slip right out of your arms. That would be a terrible feature to have built into the nervous system. So having this reflex, having this heuristic may have served a very beneficial function for a lot of human history, even still, perhaps. An alternative explanation is that if you actually look at some of our closest primate ancestors, they also have this reflex. But many of other primates actually have much longer, almost finger-like toes. And so if you were to curl when being surprised or something was touching your foot with really long toes like that, it would actually grasp something. So the alternative explanation is this is actually an ability that you see in most primates, humans included, except humans have much highly reduced toes because, well, in part it's an engineering problem where we stand up on 2 feet. Having really large toes actually gets in our way. If you want to learn about all this stuff, you can take one of my upper level courses where we go over a little bit of evolutionary theory, stuff like that. But this is a heuristic. This is something that you see built in from very early on. I'll give you another example. Imagine the following. You meet someone you're dating, okay, and you meet someone that you're really attracted to. You really like them. You get along well. You decide to go out to dinner. You learn a little bit more. You like each other. You decide I'm comfortable enough. I'm going to go spend some time with this person. Maybe you're kissing, stuff like that, watching Netflix. Then you're sharing some personal stories about yourself. You're talking about you start telling this family story about how your grandmother's known for doing this really embarrassing thing, and now all family knows about it. And the other person that you're with is like, oh, that's really weird because we actually have that story in my family too. My grandmother's super weird. And you start thinking about it and you go, wait a second, and you realize that you both share the same grandmother. You're genetically related to this person. The most common response to that scenario is disgust. Usually it's oh, I'm genetically related to you. I don't want to romantically date you anymore. I don't want to be kissing you. I don't want to be. Why have that response? Well, this is actually something that you see in not just humans. You see this in other sexually reproducing organisms. Rats do this, dogs do this, most sexually reproducing organisms. The idea is if you reproduce with someone who is genetically related to you, there is a higher chance that the offspring that you have with with that person will inherit some perhaps genetic abnormality that is particular to your family. So that is, the offspring are more likely to inherit a combination of genes that may be harmful to them. So the preferences, and again, for example, they've done experiments in rats where they house rats together, both kin and non-kin, and you give them the option to just freely mate with whoever they do. Rats, even housed with kin, will tend to seek out and attempt to mate with individuals that are genetically dissimilar to them, that are genetically different from them. The idea is that this kind of incest disgust, this aversion to incest, may actually protect people from, again, the problem of having children with genetic kin. So that is a heuristic. It's a very well incest disgust is a very well established heuristic. So here's the argument that I want to make, and this is how I want to connect this intro to last time. A heuristic really is a cognitive bias. Remember that a cognitive bias is a tendency to think or behave in a certain way that deviates from a standard of good rationality or good judgment. Many of the cognitive biases that I described last time fit this same description of a rule of thumb, something that you do in a particular situation to solve a problem. Think about authority bias. Authority bias is a quick, efficient solution to really several problems. You have the problem of, when you're relatively younger, you don't know much about the world. So if you see someone who seems to have more expertise, who is a caregiver, who is trained on something, you assume, hey, I want to listen to this authority. We have a tendency to go to authorities to learn things that we do not understand. That is a bias that has historically helped us. You should do that for a lot of things. But because it's quick and efficient, sometimes it doesn't work as you hoped it would. And so that's where these heuristics can go wrong, is they are good standard response, but they don't always apply. This is the same for something like confirmation bias. Remember that this is that tendency to search for, identify, and share information that confirms something that you already believe. So that is, if you already believe that vaccines are ineffective, you're more likely to pay attention to and share information about vaccine ineffectiveness. Why have this? Why is this a good standard response? Well, one explanation that I've heard, I encourage you to read some of those supplementary materials that I said I posted to Blackboard last time on confirmation bias. But one of the explanations behind confirmation bias, how it's functional, is that if you share information that supports what you already believe, first off, it might strengthen your ability to argue for that belief that you have. But then also, if you're sharing this information, you're more likely to convince other people of the same thing that you believe. So sharing information that supports what you believe is going to get someone else to buy into what you believe. And that is useful for actually building up groups, coalitions, alliances, groups of people to accomplish something. If everyone believes the same thing, It's usually often easier to coordinate action within a group. Confirmation bias is a very interesting heuristic to study. I recommend you look into it if that's something that gets you going. All right. I want you to keep heuristics in mind as we move into this next section. You should be asking yourself, as you learn about neurons and the nervous system, how might you use these basic parts, these basic biological principles and parts? We'll learn about neurons and neurotransmitters and how it sends an electrical charge across an axon. How could you potentially build a heuristic using this biological equipment? If you can answer that question for yourself, you're ahead of the pack. All right. That's all that I have for now. If you have questions as you go through the content, again, I realize biology is tough for some people. If you have questions and you need something else gone over, please email me. I'm happy to help you. If you start thinking about your research proposal, I'm willing to help with that as well. So please contact me with anything that you need. All right. Till next time.